Hello everyone, my name is Ning Li. I am a master student of Nankai University in China, majoring in computer science and technology. The topic of my presentation is a benchmark of ocular disease intelligent recognition, one shot for multi-disease detection. This is the main content of my report. Fundus diseases are the leading causes of blindness among human beings worldwide. Among them, diabetic retinopathy, glaucoma, cataract and age-related macular degeneration are the most popular ophthalmic diseases. These ophthalmic diseases have become a serious public health problem in the world. Most importantly, the ophthalmic disease has irreversible properties which could cause unrecoverable blindness. Timely fundus screening can avoid these problems. However, there are still some problems with the existing fundus screening. First, manual screening of fundus images is not only time-consuming but also labor-intensive, and medical resources are seriously unbalanced. Second, most of the identification models only concentrate on one ophthalmic disease, and most of the data set they use provide annotations for only one kind of ophthalmic disease. However, in real scene, a patient may have multiple fundus diseases. At last, existing data sets are based on a fundus image, but in real clinical scenarios, ophthalmologists usually diagnose patients with information from both eyes. To solve the problem above mentioned, in this paper, we release a publicly available data set for multiple ophthalmic diseases detection. In this table, we have sorted out some of the existing fundus image datasets. Compared with other datasets, our dataset is the only publicly available multi-label dataset with a larger scale. Next, I will introduce our dataset from the process of collection and labeling and the features of the dataset. The images of OIAODI are derived from our private clinical fundus database. The database contains more than 1.6 million images totally, and the fundus images are collected from 487 clinical hospitals in 26 provinces across China. We clean the images of our private database by filtering out duplicate images and low-quality images. Finally, we obtain 10,000 fundus images with 8 types of annotations from the left and right eyes of 5,000 patients for annotation. The work is done by the professional annotation staff and arbitration team, which took about 10 months to complete. First, 3 annotators respectively annotate the same batch of fundus images and record the results. If there is any disagreement among the 3 annotators, the arbitration team will arbitrate the results. The final annotation results shall be based on the consensus of 2 or more experts. Unlike most existing fundus image datasets which only focus on one ophthalmic disease, our dataset contains multiple ophthalmic diseases, as shown in the figure. In addition to normal eyes, we have annotated 6 common fundus diseases and other uncommon diseases. For diabetic retinopathy, there are lesions such as hard exudate, soft exudate, bleeding and neovascularization on the fundus image. For glaucoma, the ophthalmologist usually calculates the ratio of the optic cup to the optic disc. When the ratio is greater than 0.5, the patient is judged to have glaucoma. For cataract, experienced ophthalmologists compare the fundus images of patients with standard cataract photos to determine the severity of cataract patients. AMD is also a common cause of blindness in people of an advanced age, and it is closely related to drusen in the macular area. In the fundus image of a patient with hypertension, we can see that the arteriovenous diameter has a larger ratio. For pathological myopia, there are clear leopard print shapes in the patient's fundus area. Clinically, ophthalmologists may give diagnosis results of various diseases by observing one fundus images. Therefore, as a dataset containing multiple fundus diseases, our dataset is closer to clinical application scenarios. In real clinical scenarios, ophthalmologists usually diagnose patients with information from both eyes. In order that the related work performed on our dataset can be better applied to realistic scenes, our dataset contains fundus images of the left and right eyes of patients. In the process of feature extraction of the image, we have to balance the correlation between the two eyes and their respective characteristics. This makes the classification task on this dataset full of challenges. The ultimate goal of our dataset is to perform multi-label classification of patients using fundus images of both eyes. This figure shows some images of the patient's left and right eyes. In addition to providing researchers with fundus images of the left and right eyes of patients, we also provide age and gender of each patient and the diagnostic keywords of ophthalmologists for each fundus image. These information can help researchers better perform multi-disease classification tasks and can also help them perform some more detailed research based on the dataset, such as generating textual diagnosis and age predicting based on fundus images. The OIAODIR dataset consists of 10,000 fundus images from 5,000 clinical patients. We split the dataset into three parts, i.e. the training set, the off-site test set, and the on-site test set, which contains 3,500, 500, and 1,000 patients, respectively. The training set is used for training deep networks, and the off-site test set could be used as the validation set for model selection. The generalization ability of the deep network is evaluated on the on-site test set. The proportion of images per category in the training set and test set is summarized in the table above. We can observe that there exists serious class imbalance in OIAODIR, which is challenging for multi-label diseases recognition. In order to establish benchmark performance on our proposed OIAODIR dataset, we selected 9 currently popular deep convolutional neural networks to evaluate their performance on the dataset. The figures above shows the details of our modified network. Firstly, different from traditional image datasets used for diseases screening, the status of patients take into account both left eyes and right eyes at the same time. Therefore, the inputs of the network are 2 fundus images and the corresponding ground truth. Furthermore, to find a better baseline feature fusion method, we evaluated 3 feature fusion methods, including element-wise multiplication, element-wise sum, and concat. Secondly, it is multi-label classification task rather than single-label. We added 8 classifiers for 2-class classification behind the last fully connected layer of each network to achieve the purpose of multi-label classification. We selected 9 currently popular deep convolutional neural networks as the backbone network. We use 4 evaluation metrics, including kappa, F1 score, AUC, and their mean value, denoted as final score, to evaluate the performance of multi-label classification networks. In the table right, we mark the top 3 results of each feature fusion method with red, green, and blue respectively. We find that compared with the other 2 feature fusion methods, the experiments using element-wise sum feature fusion method gets better comprehensive performance. The figure left shows the comparison of experimental performance with different feature fusion methods. Experimental results show that simply increasing the depth of the neural network alone cannot improve performance. However, increasing the width of the network can bring certain improvement. In order to learn the classification of image samples, we performed statistics on the number of samples that were misclassified by the number of models on each label. We can find that most of the samples of each label can be correctly classified by at least 5 models. If the results of multiple models can be effectively integrated in the process of classifier design, we believe that better multi-label classification results will be achieved. There are some typical samples which are misclassified by most models in the figure. These images reflect some challenges and deficiencies of our dataset. We summarize 3 key points. First, image quality. The images in belong to diabetic retinopathy, in which hard exudate can be seen clearly. However, because of some lens stains and lighting problems, these images are misclassified. Second, intra-class confusion. The classification of images in B are affected and confused by various fundus abnormalities. For example, cataract prevents the model from identifying hard exudate. Hard exudation and drusen are difficult to be distinguished from each other, which makes most of our misclassified samples are difficult to be extracted valid regional features by models. Third, local features are not obvious. As shown in the images of the first line in C, the determination of glaucoma requires accurate ratio of optic cup and disc. In the second line of C, AMD requires more detailed features of the macular area. For these, we need to extract relevant local features to improve the performance of classification. Now let me summarize the content of this presentation. Firstly, we release a fundus image dataset with multi-disease annotations. The dataset contains 10,000 images from the left and right eyes of 5,000 clinical patients. Secondly, we evaluate the performance of some existing deep learning models on our dataset in order to provide a valuable reference for future related work. Thirdly, integrating multiple deep networks will be helpful to improve classification performance. And at last, the dataset OIAODIR is available at https://github.com/nikixel/oia-odir. Thank you.